Hello. In this video, I'm going to be going through the Week 4 poll for Fall 2025. This poll goes through several different data cleaning topics. The one that we're currently looking at right now is different ways of reordering and exploring data. So two of these are more associated with unique values and trying to characterize what are the unique values. One of them determines how many there is, and that's the table function. So the table function specifically goes through and counts how many of each unique value has occurred in a data set. Now, that does give you the unique information, which is what unique also does. But unique is more simple than table. It only just returns the data, actually even in the same order, but with those duplicate values removed. Whereas table produces a summary of that information. So for example, if I call the table function and I give it, hi Kira. Yep, oh, you're so sweet. Just gonna cuddle right up to me during the video. That's how she does. And let's see. So here I've got 3 unique values, but then they are repeated multiple times, right? So when I call table, I can see that there was 2 A's and 3 B's. However, if I change that to unique, I just get A's and B's. Now, I'm going to need to put these out of order for this next demonstration, so let's just rearrange a couple of those. The next function we're going to talk about is sort and order. So sort is very simple. If I call sort on this, it is going to sort the input. And I'm then going to spot some sort of error, and I'm not seeing it right now. Unexpected. Oh, there it is. I see it. There we go. Is there another one? Oh my gosh, there's another one. That's funny. I guess that's why that happened. Okay. So when I call sort now, it is rearranging these objects, but very directly. Order allows us to kind of create an intermediate vector that could be used to do the ordering. So for here, it's returning 1, 3, 2, 4, and 5. And what that refers back to is the order in which I should extract these values. So 1, 3, then 2, then 4, and then 5. So that is me getting the values needed to put them in order. Now to use that output, we're almost always needing to then use it as part of an extraction. But if I do so, I get that same output as sort. And you may be wondering, why would I ever want to do that? And the reason is because oftentimes we're not dealing with very simple data. We're dealing with much more complicated data. And so for example, if I want to take Iris, which I guess I can just visualize that real quick. Let's just look at the head of Iris. It's going to be too large to fit on the screen. Iris is composed of 1, 2, 3, 4, 5 columns. That's 150 rows, but you're only seeing the first 6 right now. But with the order function, and I'm going to nest it inside that head just so that we can kind of see what's going to be happening. Hi, Kira. And so I'll try calling the order function on Iris inside of an extraction. And so what this is going to do, I'm just getting all sorts of pet activity today. What this is going to be doing is it is going to take this column's values. It is going to determine what is the right order of positions in there. And then it's going to tell me how to then pull those values out in the right order. And then additionally, wherever there's a tie, it will break that tie using the values in this column. And so there is kind of an iterative sorting. And so right off the bat, we can already see that this is more complicated than sort would allow for, because sort just literally takes the thing you give it and puts it in that specific order, which really only works for vectors. Although it can be used on more complicated data, it gives weird outputs for more complicated data because, well, what are you sorting on? Here is how we dictate more complicated sortings. So now that I'm saying, all right, sort first by this column, and then within that, sort by this column, I'm then using that to rearrange the rows. That's what this extraction is going to do. And then I'm just going to visualize the output using head. And when I do that, I can see that the smallest sepal length occurred at row 14. The second smallest sepal length occurred at row 9. And then that same value at 39, 43, and 42. And so that is where that secondary sorting came into play, is wherever those ties were occurring. And so they got sorted here, 2.9, 3.0, and 3.2. And then it starts going back up again in the other column. So there we go. That is this difference between sort and order. Now to just put that into the context for this poll, returns the ordered version of the data that has been sorted. So that is by itself just sort. Sort does the sorting. It's very blunt. It's very straightforward. Returns a vector of positions that could be used to sort the vector arguments provided, so like the columns that I was extracting. That is order. It's an indirect means of reordering data, and it allows us to be much more complicated and much more powerful in how we're interacting with it. Excellent coffee. Okay, next up, we are now talking about some different tools for doing partial string matching. So what I mean by partial string matching, let me just flip on over to here again, and I can actually, there we are, and that. All right, so let's clear our screen here. So partial string matching allows us to look at parts of values. So let's use the state 77 object. There we go. So here's state 77. It's got some different values describing the US states. Well, if I want to analyze like certain state names, here we are. So here are the row names of that object. And so let's say I want to search for anything that ends in IA. So that is the symbol for end of the string right there. And then IA needs to be next to the end of the string. When I do that, I get the positions at which that match is occurring. I want to point out this is a partial string match because, well, the whole value isn't IA $, it's just the end. And so this language right here is termed regular expressions, and sometimes shortened to regex, often shortened to regex, actually. But this is the pattern in which we're searching, and the function, so this one, and this one, they all use these regex patterns, but grep specifically returns the positions. And then, of course, that's very useful. I can use those positions to, let's say, extract from that, I believe it's a matrix, actually. And if I use it to extract from those matrix, there we are, California, Georgia, Pennsylvania, Virginia, and West Virginia. And it's all very powerful. It allows us to do things like just search for, maybe I don't need that into string. And so now I should get things like Indiana and Louisiana. I forgot about Louisiana. Sorry, Louisiana. And that's it. Yeah, those are the two additional ones. So yeah, so this allows us this very powerful tool for searching for data. I use this constantly. I'm often wanting to explore things. I don't often use it for data cleaning, like doing actual changes and corrections to the data for a reason that we'll specify in a minute. But it's really, really powerful for exploring. And so we have two main types that we've been talking about in class. We have grep and grepl. Grepl is the same concept, except it returns logic. And what's really nice is then you can start to string that logic together. So I could say, all right, so for states whose names contain IA, and then also, since it's a matrix, we can't use $, and also have murder rates that are, let's say less than 10. We can start to get more and more logic. And so now I have like this combination of logic, and I could even just keep stringing things together. I could have more logic if I wanted to, but in the end, like you still typically use it in a similar fashion. In the end, I'm going to probably be using it to do an extraction from that object. And there we go. So now I've combined the row name containing IA with the logic for the murder rate being less than 10 per some number of capita, I'm sure is how that's been adjusted. So that's the idea, is that grepl is, it doesn't give us the position, so it's not quite as specific, but it does allow us to start combining logic, which is really, really powerful. This next one says returns a modified version of the X argument. Well, that is this gsub function. And that one takes a little bit more explanation. We're going to have to change this code a little bit. So here I have IA as my pattern, and then the second argument in gsub is replacement. And so this is going to be replacing it with whatever I put here. So here I should just be replacing IA with IA. That was a weird sound. Now, what you'll notice is that it's actually all of that original data and row names, but with those match patterns replaced. So this is where I'm saying, like, one way to describe this is that it's returned a modified version of the X argument. So that was the X argument, and it's replaced, this was the X argument, this was the pattern, and this was the replacement. It's returned a modified version of this X argument with those patterns replaced. So IA, and so forth. gsub. Finds matches based on just parts of the compared values. In other words, partial string matching. And so the only one of these that doesn't do this is this last one we haven't talked about, which is the equals symbol. The equals symbol is a very safe way to make comparisons, unlike, say, these flexible search tools. And that's because it only matches things exactly. So here I've written this equals, so is texts equal to the row names, which means texts will be repeated. And we'll see that that's false for everything but, well, texts. And so that's got to be the entire value. So that's a whole string match. So just coming down here, it matches based on only the entirety of the compared values. Now that's not to say that we couldn't do whole string matching. So if I did caret symbol, which stands for the beginning of the string, texts, end of string, and replaced it with, I don't know, we'll just do Z. We just did a whole string matching, but that's because this is a very powerful, very flexible tool. Equals only does whole string matching. And it's just, it doesn't use regex. It doesn't use these regular expressions where symbols mean different things. So gsub, grepl, grep, they all are using these fancy patterns where their symbols have alternative meanings than their normal symbol shape. And that's what we call regular expressions. More of a definition, really. Okay, next up, we have some gsubs, just trying to get you to look at this pattern matching. First up, we have this line of code that's creating a vector. So it just looks like this. We are then doing some gsub functions on those. And let me just copy out those other ones as well. Okay, so one of these triggered a bunch of NAs to be formed, and we'll talk about that in a second. But let's just read through. So right now, these are chromosomes. If you didn't figure that out, CHR stands for chromosome. You've seen this a lot in my class, so hopefully you've realized this by now. And then frequently, when I am making files, I often use this nomenclature of the sequence that I'm talking about, and then the position on that sequence. So defining there to be a start side, and to be fair, that is something we have to just decide. It's arbitrary which side to go from. But defining a position separated by this delimiter of a underscore. Okay, so that's what this is. Marker vec is therefore a character vector. Yep, I think everyone understands that one. It is unable to be coerced into non-NA numeric values. That's definitely true. If you try to convert this into numbers, it will just say, I don't know how to convert all of these letters and numbers and symbols into a value. And so that is going to happen. There is, however, a second one that's true for, and that's this vec1. And let's check out why. So here I have a pattern. I have underscore, period, asterisk. Let's highlight it over here, I think it'll be a little bit easier to show on this screen. So underscore is obviously just going to match here. Underscore doesn't have special meaning. It's just the symbol underscore. The period, though, does have a special meaning. It stands for any character. There are actually some exceptions, but they're like special characters, like line break doesn't count, but don't worry about that too much. The asterisk is going to be a modifier. So it's also a special character, and it will modify the period. And the reason it modifies the period is because they're next to each other, not because they have a special relationship. It's just that asterisk makes the preceding character able to be repeated. 0, actually, or more times. So I could have literally an underscore at the end, and that would be a match. But I also could have underscore 1, 2, 3, 4, or underscore 5, 4, 3, 2, and those numbers are any character 0 or more times, and so those are also matches. All in all, that's going to be a match, and that's going to be a match. I'm then replacing those matches with nothing, effectively deleting those characters. Now to look at this second one, they're set up in the opposite direction. Here I have dot asterisk and then an underscore. And so the only way to complete that is, all of these could be dot asterisk. It would go start here and go all the way to the end. That's any character 0 or more times. And asterisks by default are greedy, so they extend as far as possible. However, because there was an underscore in there, the only symbol in here that matches an underscore is that one. And so that's where it's going to have to stop in order to make this pattern be a match. Again, we're then replacing that with nothing. And if you didn't get this when you're going through, please pause the video and try to predict what that means. That means that this vec1 is the sequence name, and vec2 is the position, although it's still coded as a character. And that's just because GSub does not simplify it to a number unless you specify. So going through these, vec1 is still unable to be coerced into a number. It's got a bunch of letters in it. It's not going to be able to work. Vec2 is a character vector able to be coerced into non-numeric values. So it'll be coerced into 1,234 instead of 1, 2, 3, 4, and so forth. The next two, vec1 and where are they? There it is. Vec1 underscore in and vec2 underscore in. They are both numeric vectors, although one of them is quite odd, and that is vec1 in, which consists solely of NA values. And that's because even though I successfully did convert the class and the type, I wanted to check that too. Even though I did successfully convert it, R couldn't figure out what to do with these values when converting those two numbers. And so it just said there is no applicable or available value to represent these. And so it made them NA. The one that represents chromosome and position values, that was just like the concept behind that marker vec. That's why they have those two parts. Represents the chromosome values only. Represents the position values only. And that is these two right here. So that is vec2 in, which is the same thing as vec2. However, it is coded correctly. So it is coded as a number. And finally, we have our last one, which is only NA values. Just checking through. Yeah, that should be right. Yeah, and this one wouldn't count because it's not a character vector anymore. So even if it is able to be coerced into non-numeric values, it's not a character vector. So that's the only one that's a character vector. All right, I've checked my work. Moving forward. Okay, I really like this question. I don't know how effective it is as a question for y'all, but it gives me a chance to present this. So the idea here is that I can explore some dirty data using like grep functions. Let's try that. So let's say let's go back into those row names. So we'll grep IA in the row names of state.77. Well, when I do that, I get these different positions, and I could use that in an extraction to visualize what those positions were and print them off on the screen. This is great for exploration, But if I wanted to change the values, like if I'm using that and I overwrite it, well, they're not all California. Sorry, Californiae. They're not all that value. And so this would be a terrible choice. I've just kind of broken my object. Now everything's California. So using grep is great. It allows you to do very flexible analyses, but it's often kind of dangerous. Now, I think in this example, that was obviously the wrong thing to do, but here's a more realistic example. Here I am searching through my color column. This was from the student data where it was like who said their favorite things. However, some people said like blue and navy blue and light blue and green and blue and blue. And so when I do this search, it pops up all of those different values, and that's great. It's great for exploring. But if I replace them all with blue, that's kind of dangerous because not all of these should be blue. Some of them, like, maybe I need to even be just more specific. Like there's a pretty big difference between blue and light blue. There's a pretty big difference between blue and navy blue. And yeah, we have to often make decisions when cleaning data, like what are kind of the acceptable levels of differences, especially within categorical data. However, simply searching for blue can be quite dangerous in itself. And this is not, there's not a cut and dry answer here. It is a strategy. It is something that you just kind of have to balance, and you have to know your data, and you have to be conscious and just thinking. It's the fun part, I think. I think it's, you make important decisions, and that's true. Data scientists have to make important decisions quite often. We can't be purely unbiased, and that's something I always really try to own up to, is wherever my analysis has affected the outcomes. I think that's really important for being a good, honest scientist. But anyways, a very effective way to then clean the data that maybe was based on an exploration is to do a whole string matching. So this whole string matching is much safer in the sense that this replacement is only going to happen if blue is a exact match. So here, capital B blue is being replaced with lowercase blue, which R can interpret. And additionally, light blue with a capital L and a space is being replaced with light blue, which again, R can interpret. That's why we see these colors. So that's really the safety, that the safety is whole string matching has to match exactly, whereas partial string matching is flexible and powerful, but can have unintended consequences. And like if your data changes, then all of a sudden what used to work, like maybe I only had people who were indicating blue who contained the letters LUE, but the next time somebody submits an answer that's green and blue, well, all of a sudden my assignment, if I was assigning here, doesn't work anymore. And that's why it's dangerous. This next one is just showing you the difference between lazy and non-lazy operations. In this particular example, we are taking this values and somehow making these using gsub. Well, if we look at them, we're clearly starting a match here, ending a match here, and then replacing it with nothing. That's triggering it to effectively delete that text. This one, same thing, except it just stopped here. Now, please note these are different links, and so clearly we're going to need some sort of expanding symbol in order to make that flexible. Here, we can see that there is CHR, and then there's literally nothing here, and then there's an underscore. Okay, so anytime we see kind of like that level of flexibility, we should be expecting either an asterisk or a plus symbol. In this particular situation, since I am starting off my match with CHR, and then I am looking for an underscore, 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 no underscore, but probably not the right answer, because dot dot would only work till here. This one would work with dot dot, but this one would not work with dot dot. This one would not work with dot dot. It would trim off that one. So it's definitely not that choice. So the rest of them all use an underscore, and so clearly something needs to allow us to do this. Well, the difference between this one and this one is that here, this underscore is immediately adjacent to the CHR. Here, the underscore is separated by a 1. And so if I was, say, to do a plus symbol here, this one would not work, because in that situation, a plus would require there to be something here. And so that's not an option either. However, what are maybe some viable options, like once you've kind of gone through these, are this one and this one, because they both contain these asterisks that allow for a flexible match. The difference being, this one has a lazy modifier onto the asterisk, and this one does not, which makes that asterisk greedy. The difference between greedy and not greedy is, and lazy, I guess, is that the greedy asterisk will extend as far as it can to complete a match. So here, we start at CHR, and then the asterisk, the dot asterisk combination is going to start. So any character 1 time, any character 2 times, 3 times, 4 times, 5 times, 6 times, 7 times. But after 6 times, there's an underscore, and so that's a match. Well, an asterisk allows for 0 or more, and so 6 is 0 or more, and then an underscore. That's a match. But that's not what we wanted, right? We wanted it to stop here. And so the difference is with CHR dot asterisk, CHR dot any character 0 or more times, but be lazy about it. Here's 1 character, and that's it, because then it can complete the match, and the lazy means it stops. It doesn't continue down to the second underscore. And so that's why this one's the answer, because that match stopped before it was completed. Or before it was not before it completed. It did complete, but before it could have completed a longer match. And that's the end. I do hope that helped. Some things that my TAs pointed out that students were struggling with is especially some of these concepts of how I could use grep and grepl and things inside of a extraction. So maybe go review that if you're struggling there. I did give you some examples over here of how we could do that, so I hope those examples help. There was also a long video, that one took a while, of me going through all those questions that were in the Tuesday practice session. So go into there and give it some more practice. And it's very easy to go in and make up your own kind of questions. Like, all right, I want to go in, I want to find only things with hoses in them. Wow, that was where my brain went. Cool, I'm going to end the video now. Thank you, and have a good day.